We're going to demystify how these cutting-edge models actually pull off this trick of transforming pure, unstructured noise into stunning, high-resolution images, like a fully realized car. And we'll see exactly how leveraging the architecture of transformers, specifically something called Scalable Interpolant Transformers, makes this massive leap in fidelity possible.
Meet the Diffusion Transformer, replacing the UNet.
You know, for the longest time, the UNet was just the undisputed king of diffusion backbones. But that whole paradigm has shifted. Diffusion transformers, or DITs, have successfully replaced traditional convolutional units by essentially adapting vision transformer best practices. And crucially, researchers prove this massive correlation between network complexity, which is measured in G-flops, and the resulting sample quality. Simply put, when you scale up a transformer backbone, your generated images get significantly, noticeably better.
So how does the DTT actually work? It fundamentally operates in three main steps. First, it takes a latent representation of an image and patchifies it into a sequence of vectors. Second, it processes those vectors through a scaled dot-product attention loop. This is really where that core transformer magic happens. And finally, it unpatchifies those vectors back into spatial data to reconstruct the image. It's essentially treating image generation exactly like a sequence-to-sequence problem.
Moving along to Section 2. Unpacking flows and diffusion, the math of generation.
The underlying math here is grounded in some truly elegant calculus. Standard diffusion relies on stochastic differential equations, or SDEs. Basically, it gradually adds noise in a forward process. Imagine turning a crisp image of a dog into complete television static. Then, the model learns a reverse process. It uses what we call the score function as a guide to carefully step backwards, remove that noise, and flawlessly reconstruct the data.
But we run into two distinct paradigms here when we talk about time. On one hand, flow models interpolate between noise and data over a strict, finite time interval, usually just 0 to 1. Standard diffusion models, on the other hand, define a forward SDE that, theoretically at least, must run to infinity to actually reach a pure Gaussian noise distribution. And, as you might guess, dealing with an infinite horizon can be pretty computationally tricky.
Which brings us to a really crucial alternative, flow matching. This completely frees us from those strict infinite Gaussian constraints. It lets us map any arbitrary initial distribution directly to an arbitrary data distribution. You aren't just stuck mapping from noise anymore. You can map from low resolution to high resolution, or from unperturbed cells to perturbed cells. It is just incredibly powerful.
Section 3. Score, velocity, and interpolation. This is how we steer the generation.
To unify all these ideas, researchers formalize something called the stochastic interpolant. Think of this as a sort of overarching framework for constructing continuous mappings between arbitrary distributions. It defines a smooth interpolation path, but here's the kicker. It combines that path with a Gaussian latent variable, where a carefully tuned diffusion coefficient controls exactly how much noise is injected along the way. This unified framework gives engineers immense design flexibility. You can tune exactly how the model travels from point A to point B.
Within this whole framework, you really need to know two massive concepts. First, the score function. Its entire job is to point towards higher data density, to remove noise during that reverse SDE we looked at earlier. Second, the velocity. This defines the mean deterministic trajectory. It's the actual literal path of the interpolant from noise to data. So score is about navigating the noise, while velocity is about the direct path forward.
But here's the absolute most beautiful mathematical takeaway from this framework. The velocity field and the score have a simple linear relationship. Because they're linearly linked, we get highly efficient model parameterization. The network can simply be trained to predict the velocity. From there, it mathematically derives the score without breaking a sweat, giving us the exact tools we need to solve the reverse SDE and generate our image.
Okay, Section 4, Interpolant Transformer Architecture, or building the SiT.
Enter the Scalable Interpolant Transformer, the SiT. To see if this math actually scales up, researchers didn't just invent a new architecture from scratch. The SiT directly borrows the proven backbone of the diffusion transformer we talked about in Section 1. You've got your time and text prompt embeddings coming in, mapping directly through the attention loop blocks.
The process kicks off exactly like a standard vision transformer. It takes a cropped image, or the latent representation of it, and patchifies it. It chops it up into a grid and flattens it out into a sequence of vectors of length L. Using this exact same embedding strategy is exactly what makes the architecture so robust and scalable.
And when you pass these flattened patches through the transformer layers, meticulously conditioning them on the time step in your text prompts, SiTs achieve some incredibly high-fidelity synthesis. I mean, just think about this progressive generation of a koala, going from these early, noisy, blurry shapes all the way to absolute photorealism. It's truly wild to see the model perfectly navigate the trajectory we mathematically laid out for it.
Section 5. Sampling and Classifier-Free Guidance. Achieving Fidelity.
Now, time for an engineering reality check. In theory, continuous time generation assumes perfect, infinite mathematical solutions to our differential equations. But in the real world, running inside a GPU, we obviously can't solve these perfectly continuously. We have to use discrete time sampling. And here we have a choice: deterministic solvers, like the Euler scheme, or stochastic sampling, which actively injects and removes noise at each step to fix compounding errors. Thankfully, recent finite time analysis has successfully placed rigorous upper bounds on these errors, basically proving that discrete sampling is entirely mathematically sound.
To further boost the quality during this discrete, step-by-step sampling, we use a neat trick called Classifier-Free Guidance, or CFG. CFG modifies the sampling process on the fly. It calculates a velocity prediction conditioned on your text prompt, calculates an unconditional one, and then uses a fixed scale factor to essentially exaggerate the difference between the two.
So what does that actually mean in practice? Well, it deliberately pushes the velocity field further in the direction of your specific prompt. This guidance fundamentally alters the trajectory toward perceptual relevance, and the result? You get these stunning, highly scaled outputs, like these hot air balloons. The model isn't just guessing what a balloon looks like, it's mathematically forced to follow the trajectory that maximizes the features of the prompt.
And finally, Section 6. Connections to Related Works. The Grand Unification.
So what should you really take away from all of this? Basically, SiTs and stochastic interpolants aren't just some incremental update. They serve as this grand unifying framework, bridging continuous normalizing flows, rectified flows, and score-based diffusion, all under one modular transformer umbrella. They expand directly on the latent diffusion model framework we already know and love. They prove that flow models scale beautifully with compute. And perhaps most excitingly, they aren't just for images. The math applies perfectly to probabilistic forecasting and sequential modeling, too.
Which leaves us with a truly fascinating question to ponder as we wrap up. We've seen that we're no longer limited to just mapping pure Gaussian noise to an image. If we can now optimally and efficiently transport any arbitrary distribution to another using these scalable interpolant transformers, what complex, multimodal realities are we going to seamlessly generate next? Are we talking video, full 3D environments, drug discovery pathways? The math is absolutely ready for it.